Hello, welcome back. I'm John, an old YouTuber. Let's try to continue, but it's very hot in my living room and I'm a little bit tired. It's like 30 degrees again and I'm getting very sleepy. I'm getting very sleepy in this when it's so hot because I did not sleep enough again tonight. Yes, I did buy another Acer gamer computer I will get next week. But I like to read about this type of memories. But this is 21 pages. That's a very long words. I think that's too long for YouTube. Yes, it's early evening soon, so but still have power on the camcorder, so let's try read it. And of course I not understand everything of this because it's very high level technical information and I only have an old high school degree that's like, I don't know, 25 years ago, many years ago. Yes, like 25 years ago. So, but of course I can read the English, but I think you need some kind of higher level education to understand this into engineering or computer science. Yes, let's try read it.
Synchronous Dynamic Random Access Memory. SDRAM Memory Module Synchronous Dynamic Random Access Memory, Synchronous Dynamic RAM or SDRAM, is any DRAM where the operation of its external pin interface is coordinated by an externally supplied clock signal. DRAM Integrated Circuits, ICS, produced from the early 1970s to early 1990s, used an asynchronous interface, in which input control signals have a direct effect on internal functions only delayed by the trip across its semiconductor pathways. SDRAM has a synchronous interface, whereby changes on control inputs are recognized after a rising edge of its clock input. In SDRAM family is standardized by JEDEC. The clock signal controls the stepping of an internal finite state machine that responds to incoming commands. These commands can be pipelined to improve performance, with previously started operations completing while new commands are received. The memory is divided into several equally sized but independent sections called banks, allowing TheDevice to operate on a memory access command in each bank simultaneously and speed up access in an interleaved fashion. This allows SDRAMs to achieve greater concurrency and higher data transfer rates than asynchronous DRAMs could. Pipelining means that the chip can accept a new command before it has finished processing the previous one. For a pipelined write, the write command can be immediately followed by another command without waiting for the data to be written into the memory array. For a pipelined read, the requested data appears a fixed number of clock cycles, latency, after the read command, during which additional commands can be sent. Contents. History. Timing. Control signals. Command signals. Bank selection, ban. Addressing, a 10 /n. Commands. Construction and operation. Command interactions interrupting a read burst. Burst ordering. Mode register. Auto refresh. Low power modes. DDR's DRAM prefetch architecture. Generations SDR PC66. PC100. PC133. DDR. DDR2. DDR3. DDR4. DDR5. Failed successors. Rambus DRAM, a DRAM. Synchronous Link DRAM, SLDRAM. Virtual Channel Memory, VCM, SDRAM. Synchronous Graphics RAM, SGRAM. Graphics Double Data Rate SDRAM, GDDR SDRAM. High Bandwidth Memory, HBM. Timeline SDIM. SGRAM and HBM. See also. Notes. References. External links. History. 800 DRAM ICS on APC 100 DIMM package. The earliest DRAMs were often synchronized with the CPU clocked, and were used with early Intel processors. In the mid-1970s, DRAMs moved to the asynchronous design, but in the 1990s returned to synchronous operation. 1, 2. The first commercial DRAM was the Samsung Kilometer 48 SL2000 memory chip, which had a capacity of 16-bit. 3. It was manufactured by Samsung Electronics using ACMOS, complementary metal oxide semiconductor, fabrication process in 1992, 4, and mass-produced in 1993. 3. By 2000, SDRAM had replaced virtually all other types of DRAM in modern computers because of its greater performance. SDRAM latency is not inherently lower, faster access times, than asynchronous DRAM. Indeed, early SDRAM was somewhat slower than contemporaneous burst EDO DRAM due to the additional logic. The benefits of SDRAM internal buffering come from its ability to interleave operations to multiple banks of memory, thereby increasing effective bandwidth. Today, virtually all SDRAM is manufactured in compliance with standards established by JEDEC, an electronics industry association that adopts open standards to facilitate interoperability of electronic components. JEDEC formally adopted its first SDRAM standard in 1993 and subsequently adopted other SDRAM standards, including those for DDR, DDR2 and DDR3 SDRAM. Double Data Rate SDRAM, known as DDR SDRAM, was first demonstrated by Samsung in 1997. 5. Samsung released the first commercial DDR SDRAM chip, 64-bit, 6, in June 1998. 7, 8, 9, followed soon after by Hyundai Electronics, now SK Hynix, the same year. 10. SDRAM is also available in registered varieties, for systems that require greater scalability such as servers and workstations. Today, the world's largest manufacturers of SDRAM include Samsung Electronics, SK Hynix, Micron Technology and Nanya Technology. Timing. There are several limits on DRAM performance. Most noted is the read cycle time, the time between successive read operations to an open row. This time decreased from 10 ns for 100 MHz DRAM, 1 MHz equals Hz, to 5 ns for DDR400, but has remained relatively unchanged through DDR2-800 and DDR3-1600 generations. However, by operating the interface circuitry at increasingly higher multiples of the fundamental read rate, the achievable bandwidth has increased rapidly. Another limit is the cache latency, the time between supplying a column address and receiving the corresponding data. Again, this has remained relatively constant at 10-15 ns through the last few generations of DDR SDRAM. In operation, cache latency is a specific number of clock cycles programmed into the SDRAM's mode register and expected by the DRAM controller. Any value may be programmed, but the SDRAM will not operate correctly if it is too low. At higher clock rates, the useful cache latency in clock cycles naturally increases. 10-15 ns is 2-3 cycles, CL23, of the 200 MHz clock of DDR400 SDRAM, CL4-6 for DDR2-800, and CL8-12 for DDR3-1600. Slower clock cycles will naturally allow lower numbers of cache latency cycles. SDRAM modules have their own timing specifications, which may be slower than those of the chips on the module. When 100 MHz DRAM chips first appeared, some manufacturers sold 100 MHz modules that could not reliably operate at that clock rate. In response, Intel published the PC100 standard, which outlines requirements and guidelines for producing a memory module that can operate reliably at 100 MHz. This standard was widely influential, and the term PC100 quickly became a common identifier for 100 MHz DRAM modules, and modules are now commonly designated with PC prefixed numbers, PC66, PC100 or PC133, although the actual meaning of the numbers has changed. Control signals. All commands are timed relative to the rising edge of a clock signal. In addition to the clock, there are 6 control signals, mostly active low, which are sampled on the rising edge of the clock CKE clock enable. When this signal is low, the chip behaves as if the clock has stopped. No commands are interpreted and command latency times do not elapse. The state of other control lines is not relevant. The effect of this signal is actually delayed by 1 clock cycle. That is, the current clock cycle proceeds as usual, but the following clock cycle is ignored, except for testing the CKE input again. Normal operations resume on the rising edge of the clock after the one where CKE is sampled high. Put another way, all other chip operations are timed relative to the rising edge of a masked clock. The masked clock is the logical end of the input clock and the state of the CKE signal during the previous rising edge of the input clock. CS chip select. When this signal is high, the chip ignores all other inputs, except for CKE, and acts as if an NOP command is received. DQM data mask. The letter Q appears because, following digital logic conventions, the data lines are known as DQ lines. When high, these signals suppress data I/O. When accompanying write data, the data is not actually written to the DRAM. When asserted high 2 cycles before a read cycle, the read data is not output from the chip. There is 1 DQM line per 8 bits on AX16 memory chip or DIMM. Command signals. RAS, row address strobe. Despite the name, this is not a strobe, but rather simply a command bit. Along with CAS and WI, this selects one of 8 commands. CAS, column address strobe. This is also not a strobe, rather a command bit. Along with RAS and WE, this selects one of 8 commands. WI, write enable. Along with RAS and CAS, this selects one of 8 commands. It generally distinguishes read-like commands from write-like commands. Bank selection, BAN. DRAM devices are internally divided into either 2, 4 or 8 independent internal data banks. 1 to 3 bank address inputs, BA0, BA1 and BA2, are used to select which bank a command is directed toward. Addressing, a 10/n. Many commands also use an address presented on the address input pins. Some commands, which either do not use an address, or present a column address, also use a 10 to select variants. Commands. The SDR's DRAM commands are defined as follows: xrasgaswebin a 10 and command hxxxxxx command inhibit, no operation, luxx no operation ulxx burst terminate, stop a burst read or burst write in progress or bantle column read, read a burst of data from the currently active RAL or band column read with auto pre-charge, as above, and pre-charge, close row, window null bantle column write. Write a burst of data to the currently active RAL or bank column write with auto pre-charge, as above, and pre-charge, close row. Window null bank proactive, activate open of RAL for read and write commands or bantlux pre-charge, deactivate, close, the current row of selected bantlux pre-charge all, deactivate, close, The current row of all banks loops is auto-refresh. Refresh one row of each bank, using an internal counter. All banks must be pre-charged. LLLL00 mode load mode register. A 0 through a 9 are loaded to configure the DRAM equip. The most significant settings are cache latency, 2 or 3 cycles, and burst length, 1, 2, 4 or 8 cycles. All DRAM generations, SDR and DDRX, use essentially the same commands, with the changes being additional address bits to support larger devices. Additional bank select bits. Wider mode registers, DDR2 and up use 13 bits, a 0 or 12. Additional extended mode registers, selected by the bank address bits. DDR2 deletes the burst terminate command, DDR3 reassigns it as ZQ calibration. DDR3 and DDR4 use a 12 during read and write command to indicate burst chop, half-length data transfer. DDR4 changes the encoding of the activate command. A new signal ACT controls it, during which the other control lines are used as row address bits 16, 15 and 14. When ACT is high, other commands are the same as above. Construction and operation. For example, a 512 MB DRAM DIMM, which contains 512 MB, might be made of 8 or 9 DRAM chips each containing 512 bit of storage, and each one contributing 8 bits to the DIMM's 64 or 72-bit width. A typical 512-bit DRAM chip internally contains 4 independent 16 MB memory banks. Each bank is an array of 8,192 rows of 16,384 bits each. 2,048 8-bit columns. A bank is either idle, active, or changing from one to the other. 6. DRAM memory module, Zoom. The active command activates an idle bank. It presents a 2-bit bank address, BA0 BA1, and a 13-bit row address, a 0 or 12, and causes a read of the row into the bank's array of all 16,384 column sense amplifiers. This is also known as opening the row. This operation has the side effect of refreshing the dynamic, capacitive, memory storage cells of that row. Once the row has been activated or opened, read and write commands are possible to that row. Activation requires a minimum amount of time, called the row to column delay, or TRCD, before reads or writes to it may occur. This time rounded up to the next multiple of the clock period, specifies the minimum number of wait cycles between an active command and a read or write command. During these wait cycles, additional commands may be sent to the banks. Because each bank operates completely independently. Both read and write commands require a column address. Because each type accesses 8 bits of data at a time, there are 2,048 possible column addresses requiring only 11 address lines, a 0 and 9, a 11. When a read command is issued, the DRAM will produce the corresponding output data on the DQ lines in time for the rising edge of the clock a few clock cycles later, depending on the configured cache latency. Subsequent words of the burst will be produced in time for subsequent rising clock edges. A write command is accompanied by the data to be written driven onto the DQ lines during the same rising clock edge. It is the duty of the memory controller to ensure that the DRAM is not driving read data onto the DQ lines at the same time that it needs to drive write data onto those lines. This can be done by waiting until a read burst has finished, by terminating a read burst, or by using the DQM control line. When the memory controller needs to access a different row, it must first return that bank's sense amplifiers to an idle state, ready to sense the next row. This is known as a pre-charge operation, or closing the row. A pre-charge may be commanded explicitly, or it may be performed automatically at the conclusion of the read or write operation. Again there is a minimum time, the rel precharge delay, TRP, which must elapse before that row is fully closed and